So hi everyone, and welcome to lecture 29, the last lecture for ECE3311 Principles of Communication Systems. Ooh, so this is kind of a fun lecture because, yeah, I know I have a very messed up definition of fun, but what this lecture does is very briefly leverages the tools that we have developed over the last 28 lectures into a very specific application, which is cellular telephony. So in one of my sort of preceding classes, so I teach also a course called 2305, so Introduction to Communications and Networks. We briefly brought up this concept of cellular telephony, you know, the cell site cell phones, 4G, 5G, 3G, all that jazz, right? But we don't go into really any details, at least quantitatively, of the impact of, let's say, implementing these cell phone communication sites, right? The cell phone networks. So what we're doing here, okay, in this lecture is we're going to go over this idea of, like, you know, what is cell phone technology? This is kind of like a rehash of if you've taken my 2305 class, a little bit of review, but the main thing is it's going to differentiate pretty quickly because we're going to be leveraging quite a bit in terms of, in particular, the link budget analysis we saw in lectures 27 and 28, and also kind of touch upon other technologies. Now, I wish I can go into a lot of the more crazy analytical stuff, but that's going to be completely outside the scope of this course. Okay, so first of all, let's move forward one. Okay, wow, wordy slide. Okay, but really the idea of, like, cell phone communications is actually huge, right? Ever since the 1980s, when the cell phone concept was deployed in a sort of practical sense, right, which we call first generation or 1G communications, what ended up happening is we saw how we could develop a communication network, right, that allowed for quite a few users, right, to access wireless spectrum in order to get some sort of connectivity from it. All right. So if, like, for instance, if we go to, okay, if we go to this. So up until now in this course, let's zoom in. All right. Up until now in this course, there we go. Okay. Yeah, there's my drawing too. Okay. Until now, we made this big assumption. We've assumed, okay, that every signal belongs to one user, okay, very important assumption, and has dedicated spectrum. Okay, that's huge. That's huge. So it's almost like, imagine in an ideal world, okay, no one else in the universe is using FC. You know, imagine that. It's like, oh, no. FC's mine, no one else touch it, right? So we had, even in class tests, right? We looked at class tests where we had FC1, we had FC2, we had FC3. And we had user, user, user. And we made the assumption that, okay, we'll filter out this user using a super heterodyne multi-down conversion stage receiver design, like, but we can extract out the signal at FC1 and exclude the other two. And that's it, that's all, right? So, and then we made, we looked at signal models later on. Our signal models, we had this, right? Where the only unwanted electromagnetic sort of entity, if you want, that gets thrown into our transmitted. So that's wanted. That's unwanted. Okay. And this is what gets intercepted at Rx. Okay. So we have this thing here. Again, the premise is that no one else is around. Is also in exactly spelling FC, right? So what happened is then we looked at, okay, we looked at OFDM, right? And we looked at spread spectrum like DSSS, okay. And we saw how we could divide up time and frequency, right? So we saw, like, you know, in the electro space, okay, we saw things like this, like, you know, OFDM. So that's frequency, that's time, and that's energy. Bloop, 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 bloop. Bloop, 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 right? And we had subcarriers, okay, over time. And that's for OFDM. And we also had spread spectrum, DSSS specifically, bloop, bloop, right? And we saw for power, frequency, and time, we could make like a sandwich. Something like that, where we can stack them and then use the corresponding PN sequence to extract out the desired signal and remove and not worry about the others. All right, and that's for DSSS, okay? So for the most part, our viewpoint on supporting multiple signals has been really frequency and time. So time and frequency based. Okay, so if you want to transmit, you either do one of two things. Find another channel. So find your own FC, right? Or wait until the other signal is done to use their carrier, right? So really, those are the options, both of which, sadly, do not scale, right? So if I have hundreds of people, because here's the problem. Spectrum's limited. Okay. And if I have to time slice everything, well, that also kind of sucks, because what happens if I have a lot of data? Like, it's like, you know, Like it's like I don't want to be sliced down to only being able to communicate kilobits per second when I want to like stream YouTube or upload an assignment submission or something of that nature. So that's the problem, right? So what ended up happening? Okay, so what happened is there's a trick we call frequency reuse, right? And you might say, okay, frequency reuse, I could see that, but it's a very specific context. What happens is there's another dimension to the electrospace, which is space, geography, right? So what did you learn? Okay, what did we see in lectures 27 and 28? Electromagnetic signals decrease in signal strength quite rapidly the farther away you get away from their source, right? What happens if you're very, very, very far away? You don't hear them, right? And then we saw, especially in lecture 28, we had things like thermal noise, cosmic radiation, right? So there's this omnipresent source of noise everywhere around us. And what happens is, what's actually pretty cool is if the signal becomes sufficiently weak, right, it goes below something spectrally, I'll point it out in a second, below something called a noise floor, right? So if you have an incredibly weak signal at a receiver very, very far away, what will end up happening is it may not even hear that transmitted signal, right? Right. Of course, that's why radio astronomers, they liquid cool their radio frequency front ends for their receivers, because they're trying to eliminate as much of that thermal noise from their equipment as possible, right? But for the most part, as soon as that signal, from very far away, goes below the noise floor, it looks like there's no signal present whatsoever. And what does that mean? Theoretically, if you're trying to listen to somebody else, you could listen to somebody and not experience, in a practical sense, any interference from somebody using that exact same frequency far away. That is the concept of frequency reuse. So let me show you. So this is how frequency reuse works. So what happens is, let's say this is my base station, right? Suppose here's a user for that base station. And there's a wireless signal, okay? And it's of distance d. Suppose I have a user very far away over here, okay? And here's the cell site, okay? And it communicates here, right? And it has a distance. So let's say that's D1. That's D2. And what ends up happening is, let's draw this. Because remember, unless we do some really fun tricks, which we can, but let's assume just this energy just emanates everywhere. What happens is, if the energy is omnidirectional, it propagates everywhere. Instead of this direct line, wireless energy doesn't travel like a fiber optic cable or Ethernet cable. Like, unless you design the antenna to do that, it will emanate everywhere, right? So instead of this like squiggly line, it's actually propagating everywhere, right? Okay, let me Okay, so what ends up happening is this energy begins to propagate out. But what do we know about that wavefront? What do we know about path loss? So free space gain, right? is going to be equal to lambda over 4 pi d, the distance, all that squared. And then again, that's an approximation. We do, we do have to account for other losses as well. But that d factor, what happens if d is very big? That gain is going to be very, 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 very small, right? So so that wavefront, and then likewise the same here. So let's draw what happens when the signal coming from this base station also gets intercepted by that cell phone. I'm going to draw it in blue. And we'll represent this as D3. And let's say D3 is massive. It's really, really big. What should the free space path loss be? It's going to be huge, right? The loss is going to be incredible, right? And then likewise, this is distance D4. So what ends up happening is you have these base stations. You have these base stations. They're both operating at the same carrier frequency for this communications. They're assuming that the cell phones they're trying to service are close by, and other cell phones that are using the exact same carrier frequency along with their cellular network are very, very far away. We can, in all practical sense, communicate on that same carrier frequency over and over and over again, as long as we engineer our cellular network to reuse that frequency such that all other cell sites that use that exact same frequency can't pick it up. So that's frequency reuse. And it 100% exploits the concept of the path loss, right? So frequency reuse, because of that, and if you engineer, so usually a cell site is drawn as a hexagon, right? And again, my artwork, okay? So if I have a cell site here, and I have a cell site here, and they're servicing cell phones here, okay? If I design my cellular network, right? So usually what folks do, these are all base stations. What they do is they make sure, for sure, that adjacent cell sites do not use the same carrier frequencies, as I'll explain a little bit in a few minutes later in this lecture, but we usually put them in the one after that at a minimum, probably even farther. So what we do is if we look at this on a much larger scale, we can reuse that carrier frequency, right? Carrier frequencies over and over and over again across the same geographical area. So imagine if, like, let's say the reuse factor, so instead of having a region like this where everybody has to have a dedicated carrier frequency, we can reuse like crazy those same carrier frequencies, okay? And what does that mean? So here, if I had n carrier frequencies, okay, then I can have n users supported, okay? Here, I have n carrier frequencies, okay, but I can reuse them m times. You get it, right? So it'd be n times n, okay, user supported. Clearly an increase in user capacity, right? So this cellular concept is actually pretty powerful stuff because of exactly that. So this makes the idea of everybody having a cell phone that can operate at very high data rates viable, right? But there are, of course, a lot of challenges. Don't get me wrong. It's like, oh, well, we're going to do frequency reuse. We're all set here. No. No. Not that easy, okay? Okay, so the hexagonal things that I drew, they're called cells. And at the center of them, at least conceptually, there's a cell phone base station. Some cases, what happens is you could have cell sites at the edges and beam inwards to cellular users, but for the most part, the cell site's usually at the center, okay? And what's cool about the cell concept is it scales. Is really, really cool. So first of all, we can pepper the landscape with these cells over and over and over again, use the same equipment, same architecture. We don't have to do anything custom. Very attractive, very attractive. We can just like, you know, sort of like take region, put cells, repeat. Take regions, put cells, repeat. And you just have to build out the infrastructure from there, right? Now, if let's say even within a cell, there's not enough frequencies, that does happen. Metropolitan areas, for one, are a great example. So like if you go to New York City and downtown Manhattan is covered by one cell site that can support 1,000 users, that's absolutely not going to work out. So it scales even more. Within a cell, you can put smaller cells, microcells, femtocells. You could divide and conquer the frequencies, reuse, all the way down such that every person, okay, within a specific geographical area, and then a sub-area of that, and then a sub-area of that has cellular access with an acceptable level of data rate, okay? So that's very, very attractive, okay? So when we go back to the electrospace, very importantly, we look at time and we look at frequency. That's the diagrams we saw so far, but there's also space. I mean physical space, not like, you know, outer space. So the geography, the physical location of everybody plays a role in the electrospace. So now we have 3 dimensions to play with, all right? So in terms of like providing access to resources, access, connectivity, if you will, to every user in the network, this is something called radio resource management, or RRM, okay? So like within a space, okay, so that's one dimension of the electrospace. At a specific time instant, we want to assign a specific frequency band to a specific user for them to communicate. And we want to do that for all users, okay, across a time period within a cell, and we want to do it for all cells. So this requires like a kind of a very seriously complex algorithm in order to manage who gets what frequency channel, what time, and what cell at for per user. So that's what we call RRM, right? And it's a very challenging but very exciting area of research and development to explore. There's actually one other thing why people like you know, the cellular concept. So the main thing is that notice how if we had a cell site, okay, and we have users, okay, and they're all connected. So whenever it's from the base station to the user, the mobile, if you will, right? This direction, just as FYI, for terminology's sake, this is called the downlink, or DL. If the user communicates back up from user to base station, we call that the uplink. So that's terminology that folks use in the cellular industry, okay? But what's interesting is when I want to communicate to the user, there's an assumption that folks are that make, okay, that help keep your cell phone costs low. And the assumption is, okay, keep this keep the computational complexity of this, okay, so just the implementation complexity, low, right? Because the thing is, if you have a cell phone like this thing here, right? It's got to do all this crazy fancy signal processing, digital communication algorithm stuff in order to clean up the signal once it's intercepted. Your cell phone won't be free with a paid plan, or $500, $700, $1,000, $2,000, whatever you pay for your cell phone. It's going to be way more because you're going to need more computational resources in order to implement the algorithms that we started talking about in this course. So what do? So you offload all those algorithms to the base station. So before any signal is sent over to the cell phone user, you do all your signal processing at the base station. So there are some tricks that you can do where you can even like pre-distort your data. So what that means is if you already know what the distortion is of the environment before it hits the user, you process the signal such that it does the inverse of what that distortion does, such that when it gets finally picked up by the user, the distortion and your pre-distortion cancel out, right? So one technique like that is called pre-equalization, okay? And on the other hand, when the user communicates back up to the base station, same premise, right? User doesn't do any, user just sends the signal in sort of a simple way, and the base station does all the heavy lifting in terms of the processing, right? And that makes sense because if you look at where the base station is and all the resources and the permanent power supply and you know, the computational horsepower that's available on site at the base station, why not? Because the thing you don't want is an expensive cell phone with a massive processor with a humongous form factor. You don't want a cell phone half the size of like a laptop and a power lifetime of like 10 minutes because it has to do all that processing to take a phone call. Okay, so that centralized architecture has a lot of benefits, right? And allows us to do really cool things. So going to this, that's what's really important, is the ability for, especially with a centralized architecture, to do exactly things like that. Now, whoops. So I think I drew already the cellular architecture, what it looks like, right? Just to maybe reiterate, let's take a couple of cells. What it will look like is something like this. Here's we call this an adjacent cell. Okay, at the center is the base station. And most folks know what a base station looks like, right? Some of them have been camouflaged into church steeples and trees and other things that you can tell right away, but it's an attempt by the cell phone company not to, you know, the cellular service provider not to like look like an antenna eyesore. I personally love how cell phone base stations look like, but I must be a minority. Then what you got is you got your cell phone users, right? And it's not just cell phones. Let's say you have a laptop that's connected, things like that, right? And they communicate with the base station. Boop, 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 boop. Again, remember, centralized architecture. Okay. Now, there are several things that you should be mindful of. So first of all, whenever a cell phone user, okay, let's say this, so cell phone users can be stationary, but they can also be mobile. Like imagine taking a cell phone call in your car. So what happens is, what's nice about a cell phone user is if you go into another cell, and by that, your signal strength is actually stronger in terms of the connection with the new cell than the old cell, okay? You do something called a handoff, okay? You're not permanently attached to one cell site. You can, that's why like mobile users love this. That's why with the cell phone, the mobility factor is quite attractive. So there's something called a handoff. Okay, so that's one term I want to bring up. Obviously, I mentioned about the UL, the uplink and the downlink. That's very important. I mentioned about radio resource management. But also another very important thing is these. You might say, okay, those are hexagonal lines, right? Well, yeah, sort of, but there's actually significance here. And so what does that mean? Like, why is this significant? The reason why I'm highlighting this, okay, is very important. So if you're close to a base station, then that's great. You're doing dandy, right? But suppose you're a user over here, or here, okay, or here, right? You're at the edge. Okay, so these edge users, okay, so the edge is very, very important. So that's a terminology you will hear in the cellular community as well. This is what we call a worst case scenario. Okay, and the reason why this is worst case is because you're the farthest away from the cell phone base station and you're closest to the next cell phone base station. So things like handoffs get confused, right? Your connectivity is the weakest, right? These cells could be kilometers in size, right? Like in radius. And your communications could potentially be interfered with other users from within your cell as well from other cells, right? So the edge case, the edge users are very, very important. They kind of represent, like, if you really want to make your implementation robust, you would be looking at the edge. Like the users that are closest to the cell phone base station, like, that's the ideal. You're getting full signal strength. The cell phone base station know where you are. There's no confusion whose cell you're in. But if you're the farthest away, that's kind of like, that again is the worst case scenario. Okay. So that's kind of a very, very brief explanation of what the cell phone architecture looks like from the physical perspective, like the electromagnetic perspective. Okay, before I go on into like that electromagnetic stuff, the concept of the cell phone, or like, the practical implementation of it anyway, started in the 1980s. Okay, there was a gentleman by name of Marty Cooper, and there was actually quite a few other folks involved with him at Motorola that rolled out the sort of proof of concept prototype of a cellular phone connecting to a cellular network. Well, so what do I mean? What do I mean? So this is what I mean. Up until that point, if you want to do wireless communications with anybody, you have to use a dedicated wireless technology from one point to another. It could even be like a single whatever access point, base station, whatever you want to call, but it stops there. What do you mean? The issue is, suppose I want to contact somebody who does not have that wireless equipment, but they have a regular landline telephone. Well, that's interesting. So one very awkward way is you would wirelessly communicate with somebody with the receiving technology, and then they in turn could relay, hang up on you, pick up a landline call, and that's like super inconvenient, right? Like essentially, like up until that point, a lot of wireless technologies did not integrate with the landline telephone network. So what cell phones did is they enabled a wireless mobile user to connect to the landline network and talk with a conventional landline phone without any of this inconvenient kind of broken telephone type of stuff going on. So if I'm walking around downtown Chicago, which I think one of the tests were conducted by Marty Cooper and his team, he was able to make a phone call to a wireless base station that then connected to the landline network and be able to contact somebody on a landline phone successfully. And that's what cellular technology does, right? Even nowadays, you have your cell phone, right? 4G phone, 5G phone, connect wirelessly to a base station that ultimately connects to the wired internet and access some wired server in the cloud, right? Same concept. It's the integration of the wireless medium and the wired medium, right? So starting in the 1980s, with that proof of concept, with that approach, we have first generation cellular technology, right? And that was all analog. That was like voice. It was like, hey, how's it going? You know, and then that voice signal gets converted to the landline telephone network and ultimately makes it to a landline phone and vice versa. Then in the 1990s, cellular technology then entered second generation, okay? And that's where we begin having digital communications, like text messages, obviously, and in addition to the voice communications. 3G came up in the 2000s, right? I think a lot of you were born during that time. And 3G allowed for data, not just text messages, but actual like, hey, I want to check my email. I want to do some simple web browsing. 4G came up in the 2010s, this decade, or this past decade, and that allowed for streaming services. At every generation, the data rate goes up, the capabilities increase, and the connectivity of different services, the number also increased significantly. Now in 5G, the connectivity is massive, right? Bandwidths are extreme, and the range of applications covered are huge. And it also begins to look at other types of wireless technologies to integrate them under one huge network umbrella. So you have the cellular technology, you have the Internet of Things technology, you have vehicle connectivity, you have all these different applications all under the 5G umbrella. One seamless wireless wired network integration, okay? And just a heads up, 6G, sixth generation, is already in the works. Okay, and it's people are looking at that for 2030s, right? So every 10 years, every decade, a new technology gets rolled out. So that's kind of the evolutionary progress of cellular technology. Okay, and it does a lot of things. It focuses on things like, for instance, bandwidth, connectivity, coverage, latency. So this is what I want to focus on for the remainder of this lecture. Okay. Is let's look at lectures 27 and 28 and take the lessons learned from there to see what are kind of the impacts, what are the kind of the issues, challenges that the cellular network needs to take into consideration. So the big one, the number one thing, the enemy, if you will, of the cellular network is something called co-channel interference, or CCI. Okay, so we talked a tiny bit about this in lecture 27 and 28, mostly 28, I think. And I mentioned this word also, this phrase elsewhere in the course, signal to noise ratio, SNR. This is huge. You're going to see this a lot in ECE3311. What this thing is, it's a metric. It's an assessment for a specific carrier frequency, FC. What is the ratio of the received power at the receiver, intercept at a receiver, over the noise power? So if you have very large signal power, received signal power, and very weak noise power, the chances of your signal being like difficult to decode and stuff is minimal. We saw this with respect to signal constellations, right? That cloudy diagram around every signal constellation point is rather small. Very small SNR, which means the noise power is very big for a very weak received signal power, okay? What ends up happening there is the noise is overwhelming, it corrupts and makes it very difficult to decode, and will ultimately be making wrong decisions on what has been intercepted, bit by bit, okay? So far, again, the only thing we've seen so far in this entire course, we talked a little bit about out-of-band interference, right? But we never until now looked at what happens if somebody else is using FC. Even if it's at a distance, we have not looked at anybody else using the exact same carrier frequency, okay, until now. So what CCI is if you have two users, okay, or if you have a receiver and two transmitters, one transmitter, the desired transmitter is close by, and the other transmitter is very, very far away, and they both use the same carrier frequency. Theoretically, that far, far away, undesirable transmitter is going to contribute some amount of interference to your received transmission, right? So we model it as something called the received signal to interference plus noise ratio, SINR. Okay. So this is actually makes things way more complicated. Okay. So the interference power is actually very difficult to deal with. Very, 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 very difficult for quite a few reasons. So first of all, it's like, regular noise statistically, although it's not desirable, has some specific statistical properties that allows us to design optimal receivers around it. Again, the optimal receiver design is covered in 4305. Interference, on the other hand, statistically is a lot more complicated and a lot more difficult to deal with at the receiver. Okay. So with that that becomes a problem. And this becomes especially true when you have a mobile user at the edge, especially when you have a mobile user at the edge. And remember what I mentioned about users, their hardware is low complexity. So they're dealing with interference very far away but they're closer to it than the base station, and their computational complexity is not up there to deal with it all that well, right? So that's actually a really big problem. Okay. So what we need to do, first of all, I think in this course, I think it's quite suitable. I think it would make sense, okay, to kind of go, I think, to look at assessing that impact. Okay, so let's draw a cell site. Okay, here's a mobile user, cell site, and let's draw that. And that's a base station. So here's base station 1. That's base station 2. And that's my user, right? Okay. And that's that guy. Here's D1. Here's D2. Okay. Notice, again, edge. This is an edge scenario. So what does that mean? That signal is going to be at its weakest. That signal will be at its strongest. Strongest. Yeah, that's correct. So this is the worst case scenario, right? So the question I could ask, right, is what is the SINR? Right? So we have to transmit power, receive power from 1. And we're assuming that this signal are both communicating at FC. We have the noise power, and we have I. And I here is PR2. And just a heads up, base station 2 is not intentionally communicating with the user. Okay, base station 2 could be talking with some other user, some other schmo over here. So this is completely unintentional. And effectively what it's doing is it's jamming, or has the impact to jam user from getting communications from base station 1, right? So what do we know? Well, there's a few things. So first of all, let's look at the math. Let's look at what we did. So first of all, we want to look at things like PEIRP, right? Effective isotropic radiated power. And we want to get this from 2, right? So like this is for calculating PR2, right? So what, and so you might say, well, wait, what do you mean PEIRP? So okay, so first of all, this would be the PR2. So this is actually, so this is the, shucks. No, that is correct. AKA I. And that is going to be equal to PT2, the transmit power on the same frequency. Okay, we're making assumptions on the same frequency. The gain of the antenna, okay, the transmit antenna at the base station. Now, if you look at a cellular array, if you look at a cell phone site, it looks like this. So here's the top. There's this triangular thingy, and it's like antenna box, antenna box, antenna box, antenna box. And same thing here, bloop, 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 and then bloop, 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 bloop. And you might say, what the heck is that? So what we do there, so each one of these 4 antennas form an array. And there's a trick that you can do. If you could do electromagnetic tricks, you could make, instead of an omnidirectional electrical pattern, if you phase each one differently, you can constructively and destructively combine electromagnetic energy to make it directional. You could make, remember we were talking about directional antennas, like physical, you could also do it electrically too. So if you have, this is the top view, top of those 4 antenna elements. If you phase them, right, phi 1, phi 2, phi 3, phi 4, electromagnetically, you can make what we call a beam pattern. And you might say, what the heck is that? So that's the main lobe. Okay, these are side lobes. Okay, these are nulls. Okay, what this does is, this is a beam pattern, or electronic beam steering. And what that does is, instead of having a mechanical dish that has to track a user, by doing this electronically, by just electrically phasing every antenna and the information on it, we could project energy a specific way and not in other directions. So that means energy is very focused there, but is not focused there. It's somewhat focused there, definitely not focused there. This is powerful stuff, because now this cell phone base station can focus its energy to a specific user and not have energy leak out in other directions, minimizing its impact on other users, other cells far, far away using the same carrier frequency. So this gain term can be represented by the beam pattern. Okay. All right, so that's very, 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 very important. This here, electronic beam steering, is in a bigger area called phased arrays. Completely different topic. This is like advanced signal processing, but super spectacular. All right. So this gives us, once we take the transmit power and multiply by GAT2, Okay, and so you might say, well, okay, how does that play here? Let me erase it. Let me put that user spatially somewhere else. Okay, let's say there. What this will look like is if the base station is projecting, that's a horrible main lobe. Okay, how about this? If it's projecting here, like a lot, but less there, less there, less there, and same thing here, okay? This is great because this mobile user belonging to its cell is going to get a lot of energy, and there'll be this component here is actually smaller than it could be. The worst case scenario, of course, is when this mobile user here is actually aligned, unfortunately, with this mobile user here. That's like the worst case scenario. But again, anything we can do to minimize the impact. If we have that fluke, that's unfortunate. But if we can do beam steering as much as possible to minimize that interference, that co-channel interference from another cell. Okay, so now we get this PIRP2. Okay. And then from there, the path loss, which again is going to be humongous, because if this is like, I'm going to shoot a number here, 10 kilometers, e.g., okay, e.g. means example, it's going to be tiny, and then what happens is you do the exact same calculation for, so let's say your cell phone does some beam forming. It's possible, right? So let's say PR1, what is that going to be equal to? PT1, okay, gain of the transmit antenna at the base station. So this is at base station. Free space path loss, or gain, right? And this will be much smaller. So here, that's D2. That's so that's all. That's a huge. Here it's going to be 1, right? Sorry, oh, my dear. Right. So this is going to be equal to all squared. And then let's say your cell phone also has directional antenna on the cell phone. Some do, okay? What we hope is that when we do the signal to interference and noise ratio, this we assume is a constant. Okay? What we keep our fingers crossed is this and this, okay? This is much bigger, much larger, and this is very small. Okay, and so I talked about noise floor. What would be great is if we do, like, the spectrum. Okay, the noise floor, based on how good your hardware is, okay, is like, your cosmic radiation and all other interference. That makes that noise floor. Your signal is here, okay? That's your desired signal. Oh, let's just make it a triangle. I don't want to make it accurate, but let's say that's your desired signal. And suppose that your other signal, the interfering signal, is here. Let's say that's that. So that's desired. And that's unwanted. That's your CCI. If you have that, if your unwanted signal is below the noise floor, then you're doing great, right? So the tricks that we saw here is like, obviously cell site planning is critical, right? Additionally, FCC dictates how large, like, so some of you might say, well, what happens if that cell phone site far, far away transmit at an incredibly high power? Well, what happens is the FCC, the Federal Communications Commission, dictates what they call, or define, I'm going to use define because dictates is like, well, it kind of commands, but defines transmission masks. And you might say, what's that? It tells you what's the highest power you can transmit at different frequencies. Okay. So for instance, suppose this is your center frequency, FC. This is, let's say, FC minus delta F. This is FC plus delta F. So that's some arbitrary frequency away across all frequency. So let's say the mask would be something like, you can transmit at this power at that level, at that power across that frequency band. Then your signal must decrease by this amount, this many dB, that many orders of magnitude to this part of the mask. And then it needs to decrease even more until this, okay? What this does is the mask is the upper limit that no signal can ever exceed. So the thing is, your signal does not have to have exactly this shape, but suppose that my communication system looks like this. See, I'm already in violation of the mask. So let's suppose I implement something. You saw what spectrum looked like, right? When we did PSKs and FMs and all that. Cannot, okay, looks like that, can never exceed that mask. That's how we make sure we minimize interference. All right. Okay, and sectoring, what it does is we break up, because you saw how like the top of the base station has multiple antennas on 3 sides of this triangular thing. What sectoring does is we can divide up how the beam forming is done. So let's say we take the cell site. We divide up the cell into 120-degree sectors. And we can actually do frequency reuse, like we set a subset of frequencies in each one of those sectors such that it does not interfere with other cell phones. So let's say I use a carrier frequency here. Not only is it not adjacent or to cell after that, but I even keep the sector of that cell even further away to really minimize things. Okay, folks. So with that, that concludes lecture number 29 of ECE 3311. Thank you again. This has been a great experience, and hopefully this was a very helpful lecture.